Hi, in this video we are going to look at the topic patterns in the chemical world. This topic actually consists of a lot of bonding and structures as well as some acid and base content. So one of the purpose of this topic is serving as a revision of previous knowledge. But there's also some new items you have to learn, especially related to the transition metals. But after all, you can tell by the page that it is a short topic, and I plan to spend 2 videos to cover everything. So in the first part, we are going to talk about the first 2, and the second part of the lesson, we will be focusing on the transition metal. So let's get started. Now, first of all, we try to look at the elements of period 2 and period 3, and we want to focus on their bonding and structure. So if you look at the period 2, so starting from lithium, now you can see that the type of bonding changes from metallic to covalent. So the first 2, lithium and beryllium, they are metal. Obviously, they have metallic bond within themselves. But starting from boron to fluorine, they actually have covalent bond. Now notice neon is a noble gas. It does not form a molecule. Therefore, it does not have any bonding. So for metallic bonding, it gives rise to the giant metallic structure. For covalent bonding, you know that there are 2 structures that can form from covalent bond. So for boron and carbon, they have the giant covalent structure, whereas the rest of them have simple molecular structure. Now neon is also existing as a monatomic molecule, so it also has the simple molecular structure. So this is some kind of a revision of the structure using diagrams. So for carbon, if you remember, carbon has several allotropes, right? You remember allotropes. So allotropes are different structures of the same elements, right? Different structures of the same elements. So for carbon, at least you have to note that it has graphite. So this is graphite, and this is diamond. But there are also other allotropes such as fullerene and also graphene, etc. But at least you have to know these 2, okay? And they have different properties, which I will talk about it later. Now boron, we didn't really talk about it, but at least you need to know that it actually has a giant covalent structure, okay? And therefore its physical property is quite similar to diamond. We will talk about it again later. Simple molecular structure, realize that nitrogen is N2, oxygen is O2, fluorine is F2, okay? Now for period 3, you actually see some similar pattern when compared to period 2. Again, you realize the element is changing from metallic bond to covalent bond from left to right across a period, okay? So metallic to covalent, okay? Of course, metallic bond gives rise to giant metallic structure. Covalent bond, we have giant covalent structure for silicon, and the rest of them are simple molecular structure. Okay. Again, this diagram shows you the structure. Pay extra attention to fluorine and phosphorus and sulfur, because for phosphorus they actually exist as a P4 molecule. So it's kind of like a little pyramid, right, with a triangle base, and sulfur actually exists as a S8 molecule. So usually we describe it as like a crown, okay, like a crown, okay, like the king wear a crown, okay. So it has some kind of weird shape. Why do we have to learn about the formula? It's because the formula also entails its size, right? You realize that S8 is obviously bigger than P4, right? And the size also determines the strength of Van der Waals force, and therefore determining its boiling point, etc. Because of the big size, these 2 actually exist as a solid in room temperature and pressure, despite having a simple molecular structure. The rest of these are actually gas, okay? So size does matter, all right? Now down here we have some observation, which are the periodic variation. So, or actually going back to the first sentence, we have a term called periodicity. So that refers to the periodic recurring pattern that we can observe from the periodic table. And this pattern can observe across period 2, it can also be observed across period 3 and period 4, etc. Not only do we across a period, but sometimes we also describe periodicity down the group. Alright, so these are what we can observe. This one we have mentioned, the bonding changes from metallic to covalent. The structure changing from giant metallic structure to simple molecular structure through giant covalent structure. We have the giant covalent structure sandwiched in between. By the way, what about giant ionic structure? Like, because we know that we have 3 bondings and 4 structures, right? But why don't we have giant ionic structure? Well, it's simple because we are talking about elements, right? For ionic compound, you must referring to a compound, right? They are not existing in an element, okay? Atomic radius, basically the size. So across a period, the atomic radius decrease. So going from left to right, the atom gets smaller. Down a group, the atom gets bigger. Now, down a group, the atoms get bigger. It's simple. It's easy to understand because they simply have one more occupied electron shell. With more shells, your atom becomes bigger. Now, but across a period, why the atom size decreases? This one is out of the syllabus, so I think you can only recognize it. That should be sufficient. If you really want to know why, you can come and ask me later. Now, electronegativity. This one we kind of talk about it when we talk about microscopic world too. You know, the idea is the top right-hand corner is having the highest electronegativity, right? So we always say that fluorine is having the highest electronegativity. Okay. Of course, we're neglecting the noble gas because the noble gas does not form any compound. So this one has the highest electronegativity, followed by oxygen, followed by nitrogen, followed by chlorine, etc. So if you remember this top right-hand corner, which means when element is going from left to the right, the electronegativity increases. On the other hand, when the element moves from top to the bottom, the electronegativity decreases. Okay, from top to the bottom. Okay, so always remember the top right hand corner is the one that has the highest electronegativity. Then you should be able to recall this trend. Okay, so across a period, the electronegativity increases. Down a group, the electronegativity decreases. Okay, so 2 quick practice questions. Again, pause the video. Try to go through this question or try to do it yourself before looking at my explanation. So, this one, which of the following substances have their atoms joined by strong covalent bond? So, we have to check their bonding and structure. For beryllium, it is a metal, so of course this is not the case. If you know that it is not the case, you already choose C, okay? 2 and 3 should be easy. Boron and aluminium are both group 3 elements. Which of the following statements is correct? So they both are metal. Now this one, pay attention, this is not correct because boron is actually a metalloid or semi-metal, if you recall. So it is not a metal. Giant metallic structure? No. Okay. Boron is actually having giant covalent structure. Good conductor of electricity? No. Okay. Boron is insulator of electricity. They both have the same number of outermost shell electron, of course, because they are group 3. So the answer is D. Okay, so the next part, variation in melting point. So we try to look at how the melting points of the element across period 2 and period 3. In our syllabus, we only focus on period 2 and period 3. We don't really talk about period 4 because we have the transition metal, which is a little bit different when compared to period 2 and period 3. So we only focus on period 2 and period 3. Now, I want you to focus on the red one, which is talking about the period 3 elements, starting from sodium to argon. Now, we are talking about melting point. Always remember, melting point depends on the structure and also the bonding, okay? If you have a giant structure and if you have a strong bonding holding the particles together, then it should have a high melting point. On the other hand, if you have only weak forces holding the particles or molecules together, then your melting point is low. So we try to explain all of these using bonding and structure, using what we have learned in Form 4. Now, first of all, let's look at the first three elements of period 3, sodium, magnesium, and aluminium. Now, you notice that the melting point increases from group 1 to group 3. Now, you may notice these two are very similar, but the explanation is complicated, but at least aluminium should have a slightly higher melting point than it. Okay? Now, first of all, we want to know why we have such a trend. Now, this one you have to recall the factor affecting the strength of metallic bond. First of all, you notice they are all having the giant metallic structure, right? So they are all the metal ions and the delocalized electrons are held by strong metallic bond. So if you have a stronger metallic bond, you have a higher melting point, right? So that goes to the second one, actually 1 and 2, okay? The second one. So first of all, they are all metals except boron, and you know that, I just use an example. If you compare sodium and magnesium, sodium is going to be 1 plus, and magnesium is going to be 2 plus, right? And there should be one delocalized electron, whereas magnesium should have 2, right? And because it has a lower charge, so the size should be bigger. Magnesium having a higher charge, the size should be smaller. And we say that there should be electrostatic attraction between the ion and the delocalized electron, but there are like 2 electrons for magnesium versus 1 electron of sodium. So you can tell the metallic bond is stronger in the case of magnesium when compared to sodium. Okay? Simply because magnesium has more delocalized electrons, it has a higher charge density, higher charge, smaller volume, leading to a higher charge density. And because they have a smaller size, they can pack more efficiently. So all these contribute to the stronger metallic bond. Okay? And this is why magnesium is having a stronger metallic bond, a stronger melting point when compared to sodium. And that would be the same idea goes for aluminium. And that is the same idea when we have to explain why beryllium is having a higher melting point when compared to lithium. Alright? So that's the idea. So that would be point number 2. Now point number 1, I forget to talk about it. So in general, the metals are having higher melting point than the non-metals. Okay? They have a relatively high melting point simply because they have giant metallic structure. So they got strong electrostatic attraction between metal cations and delocalized electrons. These are molecules, right? Simple molecular structure, molecules are held by weak van der Waals force. So metals in general is having a higher melting point when compared to the non-metals in general. Okay? Now, what about point number 3 here? It says that within the same group, period 2 metals have a higher melting point than period 3 metals. So within the same group, let me use an example. Let's just say we have, for group 1, we have lithium for period 2, and then we have sodium for period 3. Okay? So what it's trying to say is lithium is have a higher melting point than sodium. Okay? Both of them are group 1, and lithium is period 2, higher melting point than period 3. Okay? The reason is simple, because lithium is smaller, sodium is bigger, right? Now, both of them produce 1 delocalized electrons, but because of the smaller size, lithium has a higher charge density, and therefore they are attracted by a stronger force. Okay? This is a weaker force. Okay? So this is the reason why. That's why there is a chance that they ask you to sketch this graph, or perhaps they give you the red one and then ask you to sketch the blue one accordingly. Okay? If that is the case, you have to pay attention. For period 2 metals, they should have a higher melting point than the corresponding counterparts in period 3. Okay? So this is what you need to know. Let's look at point number 4 here. So it says that group 4 elements are having the highest melting point. Highest melting point. You can see from here, for period 3, silicon is the one that has the highest melting point. Carbon for period 2 has the highest melting point. Simple, because both elements are having giant covalent structure, so that atoms are covalently bond with strong covalent bond. If you want to melt it, you have to break essentially all the covalent bonds, which is very difficult, and that's why they have a very, very high melting point. Carbon is having a higher melting point than silicon. Now this one has to do with the size, because carbon is smaller. Carbon is smaller, okay? So think about carbon is smaller when compared to silicon. Try to make it a little bit saturated, okay? So if we have a smaller size, then the bond length, okay, will be shorter, right? The bond length will be shorter. So with a shorter bond length, the bond strength is stronger. Thinking about the two magnets are getting closer to each other, okay, then it will be stronger in terms of the attractive force. But of course, remember, it is not the two nuclei attracting each other, it is the nuclei attracting with the bonding electron, right? The bonding electron. Like nucleus attracted this electron, the nucleus attracted this electron, okay? So anyway, the shorter the bond length, the stronger the bond strength, okay? So this is something you have learned in microscopic world 1 or 2, I forgot. Okay, so the 6th point, elements are from group 5 to 0 having relatively low melting point. We kind of talk about that because they have simple molecular structure, only weak van der Waals force holding the molecules together. 7 here, molecules in period 3 are having higher melting point than the molecules in period 2. Okay, so period 3 higher melting point than period 2. Now this one, as you can see from the graph here, so period 3 is the red one, which is in general higher than the period 2 elements, right? So why is that? Now it's quite simple, because they all have simple molecular structure, so the melting point depends on the strength of intermolecular force. And in this case, they are all having van der Waals force because they are all nonpolar. So the strength of van der Waals force depends on the size of molecules or the number of electrons. So obviously, for period 3 elements, they have more electrons or they have bigger size. They have stronger van der Waals force among molecules, and therefore they all have higher melting point or boiling point when compared to the period 2 counterparts. So that's the idea. Okay? So bigger in size because of stronger van der Waals force. And the last one, this one is quite frequently asked, is about the melting point of argon, chlorine, phosphorus, and sulfur. You notice it is quite strange over here in period 3. You notice like phosphorus is having a melting point here, and then when it goes to sulfur, it kind of goes up a little bit, and then it goes down, and it goes down. Like it's quite strange. If you look at like the period 2, they kind of the same. They kind of like gradually decreasing. But why we have such a strange pattern for period 3? This one has to do with the formula of the molecule. Or we have a term called atomicity. But anyway, because like I said, sulfur is having an S8 molecule. Phosphorus is having P4, chlorine is Cl2, and argon is Ar. So you can tell the size, it should be biggest for sulfur, smallest for argon. And again, the size is directly proportional to the strength of van der Waals force, and this is why we have such a trend. Okay? Now you notice when we talk about melting point, you see there are 8 remarks, but which are the more important ones? Now if you ask me, you need to know about obviously the very basic one, metals is having a higher melting point than the non-metals, so 1 and 6 are important. You also have to know that for melting point of group 1 to group 3, you have to explain using the number of the localized electrons, or explain using the charge density, or simply the charge. Okay? You also have to talk about group 4 elements having the highest melting point because of the giant covalent structure. And also you need to know about the size of molecule, how it is related to the strength of van der Waals force, and therefore the melting point or boiling point. Okay, so these are the things you have to pay extra attention to. Okay, 1, 2, basically not 3, not 5. Okay, not 3, not 5. The others are important. Okay. Now, let's look at another graph which is talking about electrical conductivity. So, when it comes to electrical conductivity, we have to look at whether or not there is mobile delocalized electron. Okay? We don't talk about mobile ions because that one is for ionic compound, and we don't have any compound here, right? So we only want to look at if there is any delocalized electrons. So very quickly you can tell, you can see, right, all the nonmetals which having a simple molecular structure, they do not have any electrical conductivity, right? So very simple, no matter you are in period 2 or period 3, okay? As long as you are having simple molecular structure, you got no electrical conductivity. And mostly we focus on the metals, but we also have some semi-metals and also some kind of like graphite is also a very important example. First of all, you know, metals is having a high electrical conductivity in general. Non-metals are insulated except graphite and metalloids. Metalloids are boron and silicon. They have some electrical conductivity at room temperature. At higher temperature, they will have a higher conductivity. Okay. To explain that, you have to talk about the giant metallic structure. It has a sea of delocalized mobile electrons able to contribute to the electrical conductivity. Metalloids, they have giant covalent structure, but they still can contribute a little bit to the conductivity. Okay. So group 1 to group 3, you see an increase in electrical conductivity. You see, for example, from sodium to magnesium to aluminium, the conductivity increases, right? Lithium to beryllium also increases. Boron is a metalloid, that's why it does not continue to go up. Okay, so bear in mind. This is because you get more and more delocalized electrons from group 1 to group 3. Group 1 you have 1 electrons, group 2 you have 2, group 3 you have 3, right? So that's why it gets higher and higher electrical conductivity. Graphite conducts electricity because, again, it has delocalized electrons. The key is delocalized electron. Diamond, it does not, because each carbon atom in diamond actually uses all of the outermost shell electron to form covalent bond. Okay, so it bonds with 4 other carbon atoms. So we say that all the outermost shell electrons has been confined in the covalent bond, and they are not available to be contributed to the electrical conductivity. So that's why diamond has no conductivity. So so you need to know how to sketch this diagram. Now these bunch of things are molecules, they don't have any delocalized electrons. Okay, and then again, practice question. Pause the video, go through it yourself before I do it with you. Okay, let's do it. Highest melting point. Now you notice these are all metals, right? These are all metals. Okay, so lithium is having lithium plus, calcium is calcium 2 plus, potassium is K plus, magnesium is Mg2 plus. So first of all, if you want to have a higher melting point, you want to have a stronger metallic bond, you go for the ions of higher charge. So immediately I can cross out this 2. So comparing these 2, we want to look at the size, right? This one has a smaller size, this one has a bigger size, because this is period 3, this is period 4. Okay, so bigger size, smaller size. So we want to talk about charge density, right? So this one has a higher charge density, okay? Because it has a higher charge, smaller size, and therefore D would be the best answer. Question 2 here. Period 2 elements, melting point increase across the period. No, okay? Because across the period on the right hand side we have the non-metals which are having low melting point. electronegativity increase across the period? Yes, this is correct. Okay, remember the top right hand corner? That means going up and going to the right hand side will both increase the electronegativity. And C here, not correct, because the non-metals cannot conduct electricity except it's a graphite, right? All solid elements have giant metallic structure? Of course not. What about carbon? Carbon is having giant covalent structure, right? Okay, indium is a group 3 elements at period 5. Which of the following is correct? So it is a metalloid. Last time I checked, it is not. Higher melting point than aluminium? No, because it should have a bigger size. If it has a bigger size but still having the same charge as aluminium, I don't think it has a stronger metallic bond. It has a higher electroconductivity than boron. Yes, because boron is having giant covalent structure. It's a metalloid, right? But indium is a metal. So metal should have a higher conductivity when compared to a metalloid. Well, it forms a positive ion with +3 charge by gaining 3 electrons. No, it should be losing, right? It should be losing electrons, right? Okay, so the answer is C. Okay, so D, boy, C, right? Okay, so next part here is about the oxide. Okay, so now this part, actually a lot of things you have to memorize. There's not much I can explain to you. You need to recognize that the oxide of the element, actually some of them behave like an acid, some of them behave like a base, some of them actually can be behaving as acid or base. Okay, so this one you need to recognize. So first of all, I want you to look at the formula. Now some of them has more than one possible formula, but the one that underlined it is the most stable one, the one that you're supposed to write, okay, if the question asks you. Okay, so they all form oxide with different stoichiometry, but one thing is important is that you need to know the bonding. Now for group 1, group 2, group 3, they are having ionic bond. Group 3 here is predominantly ionic. Actually, it has some covalent character, but this one is out of the syllabus, you don't have to consider. Now, on the right-hand side here, they are all covalent bond. Okay, silicon dioxide covalent bond. These are all covalent bond. But talking about structure, so they have giant ionic structure here, simple molecular structure for these 3. Now, silicon dioxide is having a giant covalent structure. You need to memorize this. Okay, giant covalent structure. Okay. Now, why does it have such a characteristic? Like, why does it changes from ionic to covalent? Why is that? Now, the reason is because you need to know oxygen is a very electronegative element. Oxygen. So it has a high tendency to take electrons, to grab electrons from others. Now, for group 1 metal, group 2 metal, group 3 metals, they are kind of having very low electronegativity, or in other words, very electropositive, right? So that means these 3 elements, they don't want electrons. They want to get rid of the electrons. They want to throw away the electrons. So when the metal come across with a very electronegative oxygen, so instead of sharing electrons, they actually prefer transfer of electrons. So the metal will transfer the electrons to the oxygen, forming metal ions and oxide ions, and they will form ionic bond. Okay. Now on the other hand, on the right hand side here, these elements, because they are on the right hand side, they have a higher electronegativity, more comparable to oxygen. So instead of having a transfer of electron, they simply because the non-metal elements are not that willing to sacrifice its own electron. Okay, so they will prefer sharing electron. Now, when you share electron, you have a covalent bond, and that's why we have such a trend. Okay. Now, acid-base property of oxide. So you need to know what oxides are acidic, what oxides are basic, what oxides can behave both. And here we want to focus on the reaction with acid. So basically, how these oxide reacts with acid. reaction with alkaline, like how this oxide reacts with alkaline, and also reaction with water. Okay. Now this is actually very simple. If you have an acidic oxide, then you don't react with an acid, right? Acid does not react with an acid, right? If you have an acidic oxide, you will react with the alkaline, and you will also react with water to form an acidic solution. Okay. If you have a basic oxide, on the other hand, it will react with acid. It does not react with alkaline, and it reacts with water to produce an alkaline solution. All right. Later on, we have something called amphoteric, which is both acid and base. So that means it can react with acid, it can react with base, but it may or may not react with water. Okay, we'll talk about it later. Okay. Now let's look at these oxide. Actually, we only focus on the period 3, only period 3. Okay. We don't really look at period 2. Okay, it's a little bit strange for period 2. Anyway, so sodium oxide, magnesium oxide, these two are very basic oxide. So they react vigorously with water to form an alkaline solution. Okay, so sodium hydroxide, magnesium hydroxide. Okay, and these are obviously basic oxide. On the right hand side first, these oxide, these are acidic. So they dissolve in water to give you different acids. So strong acid for this one. This is a weak acid. This is also a strong acid. Okay. Actually, it's a weak acid. Sorry, weak acid. Okay, but they are all forming acidic solution. Okay. So obviously, if you have this basic oxide, if you treat it with acid HCl, then you will expect to see a neutralization reaction. Similarly, if you have this one, in that case, it's neutralization reaction. If you react with this acidic acid with an alkaline, then again you may expect to see an acid-base reaction. Okay. Now let's look at aluminium oxide. It's a special case. Aluminium oxide does not react with water. But it can react with acid. It can also react with a base. So that's why we call it amphoteric. Now amphoteric means both acidic and basic. Okay? But bear in mind, does not necessarily able to dissolve in water. Okay? Does not necessarily be able to dissolve in water. Now this is the case. Aluminum oxide is insoluble in water, but it can react with acid. It can also react with a base. When it reacts with an acid, then it is acting as a base. When it is reacting with a base, then it is acting as an acid. Simple as that. Silicon dioxide is again a special case. It does not dissolve in water because it has a giant covalent structure. Remember, giant covalent structure. So you cannot expect something with a giant covalent structure be able to dissolve in water. Because if it wants to dissolve in water, it has to break all the covalent bond, which is very difficult. And that's why silicon dioxide, which is essentially the sand, okay, on the beach, the sand at the seashore, they are insoluble in water. But actually they are slightly acidic, so it actually can react with strong alkalines such as sodium hydroxide, and it can react to form other products. If you know that for glass is actually made by silicon dioxide plus something else. This is also the reason why we don't use glassware, especially pipette or burette, to hold concentrated strong alkaline such as sodium hydroxide, because the sodium hydroxide is going to damage the glass, especially for pipette and burette. You don't want those accurate, delicate glassware to be damaged by the strong alkaline. Okay. This is something sidetrack. Going to the right hand side here, a bunch of equations you have to memorize. Starting from something easy. For basic oxides, they react with water to form a strong alkaline. They also react with acid to form a salt and water. In this case, this is a neutralization reaction. Okay, so these are not very difficult. For amphoteric oxide, this one, please memorize. memorize, okay? Because this is a special case. For amphoteric oxide, amphoteric substance is something that can exhibit both acidic and basic property, okay? But again, does not necessarily dissolve in water. Now bear in mind, amphoteric species can or cannot dissolve in water, okay? The definition here is simply saying that it can exhibit both acidic and basic property, okay? It has nothing to do with whether or not it can dissolve in water or not. In this case, it is insoluble in water. But some other amphoteric species might be able to dissolve in water. So this one is something you have to pay attention to, okay? Aluminum oxide is insoluble in water, okay? Well, it can show its basic property and acidic property. Now again, sometimes the question asks you to use equations to illustrate the basic property and acidic property of a particular species. So if you want to show its basic property, the best way is to add an acid, right? Because if you have a basic property, you react with an acid, right? So similar idea. If I want to show aluminum oxide having a basic property, I simply react with some acid such as HCl, okay? So this is a very simple reaction, just like a neutralization reaction, okay? But I use an ionic equation, so this is how it looks like. Of course, you can add the Cl here to balance the equation, okay? If you want to show that it has an acidic property, similar idea, reacts with a base, reacts with an alkaline, okay? Now the equation is a little bit complicated. This is the one that I expect you to memorize it, because not only you react with an hydroxide, but you also add water to balance the equation. Actually, it forms a complex ion, which is I think it's aluminate ion, right? I don't really recall the name of this. It's kind of like aluminate ions, or actually tetrahydroxyaluminate ion, okay? Alright, the third part here is acidic oxide. Now this part is a little bit complicated because we have so many kinds of acidic oxide, and different oxide forms different acids when dissolved in water. First of all, let's talk about silicon dioxide. Like I said, it is acidic, but it is insoluble in water. It can react with strong alkaline to form a silicate ion, okay, which is soluble in water, and that's why strong alkaline will damage a glass made by silicon dioxide. Phosphorus pentoxide, P4O10 here, it dissolves in water to form phosphoric acid, which is a weak acid, a weak tribasic acid. Sorry, I meant to say weak acid before, okay? So here is a weak acid, okay? So it's a weak acid. Sulfur dioxide, sulfur trioxide, pay extra attention. For sulfur dioxide, it dissolves in water to form sulfurous acid, which is a weak acid. If you have sulfur trioxide, then it reacts with water to form a sulfuric acid, which is very acidic, very strong acid, okay? Highly exothermic when you undergo this process, so be extra careful. We try not to do this step, okay, because it's highly exothermic, probably causing splashing of water together with a highly corrosive strong acid. Two different oxides of chlorine. We have dichlorine monoxide and dichlorine heptoxide. Dichlorine monoxide will form hypochlorous acid, HOCl, which is a weak acid. If you have dichlorine heptoxide, it will form perchloric acid, which is a very strong acid, okay? So try to remember these equations, and sometimes they may ask you to write equations like this, okay? Now at the back we get some multiple choice questions. Again, I'm not going to talk about these questions. If you have done it, you can always find me and check the answers. So what we have left is the transition metal, and I intended to talk about it with a separate video clip. So that's it for this part. See you later. Stay tuned.